All right, clip number 3, section 6 notes, segment relationships and circles. In this clip, we're going to do 2 examples. The one seen here in the margin, and then we're going to do this last one here at the bottom. In both cases, this is going to be an illustration of the third and final theorem we talked about. It's really just an extension of the last example we did in the last clip, where I have an intersection of 2 segments on the outside of the circle. The unique thing here is that I'm going to end up with a tangent piece, which will give us a chance to use this piece of the formula, but I'll demonstrate how it stems from the second theorem, okay, where it's going to be outside piece times the whole length of the whole segment. It's just going to end up being multiplied by itself, though. And what you're going to see here is that even though this one looks a little bit denser with the type of information that they give, the solution here is going to be pretty straightforward. Nothing really terribly complicated as far as the algebra goes. A little bit of combination-like terms, but that'll be about it. This one, however, even though it looks a little bit simpler, this one's going to end up, we're going to have to use the quadratic formula in this case, but I'll get to that in a minute. Let's start with this guy. So let me jump to the whiteboard so that we can zoom in a little bit on this figure. All right, so what are we given? We're given a circle. We're given the following secant. So a segment that passes through a circle at 2 different points. And the unique thing about this segment is that they're telling us it basically passes through the center of the circle. Meaning that the endpoints of this chord, which in this case are D and C, and somewhere out here at some point B, that D to C represents the diameter of this circle because it passes through the center, which also forces D to E to be a radius and E to C to also be a radius. Okay, and then we have some tangent piece that does this, where we got some point A up here. Fundamentally, however, this is still going to be the intersection of 2 segments on the outside of a circle. So before I even plug in the stuff that I need to know that I'm given here in the diagram, I can have the following. I have 2 segments. So segment number 1, let's focus here on AB on top. Well, according to the second theorem that we covered in the first clip, I could take the outside piece of this segment, which happens to be A to B. All of that is outside of the circle. I'm going to multiply that by whatever the whole segment is. And here's where we see that third formula at play. The whole segment happens to be all outside the circle. So it gets multiplied by itself. Well, for my second segment, now I'm going to follow the same pattern. Outside piece is going to be B to C times the length of the whole segment, which in this case is B to D. Now what we see here is this one's actually split up into 3 pieces, and that's fine. I'm just going to be adding each of those 3 lengths. But the whole segment is B to D. So this right here that you see, this is a representation of that second theorem. Outside piece times the whole segment, outside piece times the whole segment. Where we see that third theorem in play that deals with a tangent piece, like we see here, is that I get this unique situation where the outside piece and the whole segment are one and the same. So I can actually rewrite this as AB squared is equal to BC times BD. And this is where that third theorem breaks down, like the tangent piece, whatever it is, the tangent piece in this diagram, I'm going to square that length. That's where that comes from. All right, well, now let me plug in the pieces that we were given in the diagram. They told me that this tangent piece is 20 units long. They told me that this outside piece for this other segment was 8 units long. And then I know I wrote it in the margin in the notes where I said that this was R units long and this is also R units long. But be aware that in big ideas, this might be all they give you. And here's where I can make the leap to say that this must be R and this must be R. The fact that this passes through the center of the circle, it's not just some random secant. That forces each of these DE and EC lengths to be the same because they're both a radius of the circle. So actually, logically, this is required to be an element of this diagram, even though I explicitly wrote it in the margin. All right, well, now let me plug in the pieces that I'm given here. All right, well, AB is simply 20, so I'm going to have 20 squared here on the left. BC, the outside piece of the second segment, is simply 8. And then B to D, this is where I'm going to get a little bit of, something I got to deal with. the entire length of B to D, I have to add up each of these three pieces. So I'm going to have R plus 8. Right? That's just explicitly what it is. Great. All right, well, some of these pieces I can solve for. So 20 squared, or 20 times 20, is 400. On the right-hand side, let me combine my like terms in this parentheses first. Common mistake, a lot of students would kind of default to like, oh, R plus R is R squared. No, R times R is R squared. R plus R is 2R. So make sure you don't make that mistake. It's a common one, but don't make that mistake. All right, now I can distribute, because again, this is just multiplication, so I just have to make sure I multiply throughout the parentheses. 8 times 2R is 16R. 8 times positive 8 is positive 64. Left is still 400. Well, now we have a pretty traditional problem right here. Don't be afraid to use your calculator. Subtract the 64 from both sides, and I get 336 here on the left. It's equal to 16R. Divide by the 16, and I'm going to get 21 equals R. This problem I had to solve for the radius, so we were done. Be aware it might ask you like, hey, what's the length of all from B to D? So I'd have to plug that value in. Or it might be like, what's the diameter of the circle? What's the area of the circle? Both of which would need what radius is. So those are just different ways it might phrase it. Okay, but that's essentially just an extension of the second theorem on two segments intersecting on the outside of a circle. So now let's do our last example for section 6. I'm going to stay here on the whiteboard. All right, so here's what we're given. We're given a circle with some tangent piece, point of tangency at point Q, outside endpoint at point R. And then we have a secant that passes through the circle like so. And then we have endpoints of S and T for that chord. All right, so without even looking at what the diagram tells us, I know that I have outside piece times entire segment. That will end up being RQ times RQ, because the entire segment is on the outside of the circle. So I'm going to end up with RQ squared, to quote that third theorem. And then the other segment, I have outside piece times the length of the whole segment. So it's going to be R to S times R to T. So I know that has to be applied here. So now when I plug in the values, they tell me that it's 16 units from R to Q, the tangent piece. S to T, they tell me is 8 units. And then the piece that I'm solving for here is actually on the outside. It's R to S being X units. So I'm just going to plug this stuff in, just like I have before. But what we're going to find is that when my unknown's out here, I'm going to end up with the unique situation. So when I plug in RQ of 16 units, I end up with 16 squared here on the left. RS is my variable, so that's X. And then R to T, I just have to make sure I add these two pieces together, X plus 8, and I end up with this phrase. Okay, now I'm just doing the distribution here on the right, and then I can do this piece in the calculator. 16 times 16, or 16 squared, gives me 256. When I distribute this throughout the parentheses, X times X gives me X squared, and then X times positive 8 gives me positive 8X. So far, nothing terribly different than what we've done so far. But here's where we run into a unique issue that we haven't come across in a while. Up until this point, particularly in this chapter, anytime we've had like an X squared element on one side of the equation, there's been a corresponding X squared element on the left side. And when we combine like terms, they end up canceling, and then we don't have to deal with it. However, in this problem, I can't get rid of the X squared. And I cannot combine it with the other X, because I can't add or subtract X squareds and X's, just like I can't combine with addition or subtraction X's with numbers like that. And so I'm kind of stuck at this point. And if I'm trying to get X by itself to solve for it, if I were to try getting X squared by itself, I'd have an X on the other side. If I were to try and get this X by itself, I'd have an X squared on the other side. So solving for X takes on a new challenge in this case. And here's where I'm going to ask you to trust me with this first step, because I'm going to prep us for the strategy we're going to use. I'm going to take this 256 and move it to the other side of the equation. So this positive 256, I'm going to subtract it to the other side, and we're going to end up with this equation. The x squared and 8x stay the same, but when I subtracted the 256 to the other side, I get this. What we have just created is what's called a quadratic, which is something that we were very familiar with in first semester. We spent several chapters around quadratics. And all a quadratic is it involves some polynomial that has an x squared element. All right? So here's where we're going to apply the universally accepted, like, foolproof way to solve quadratics. It's called the quadratic formula. And so let me write the quadratic formula off to the side here first. Again, if you want to have this down, you will come across problems like this in your assignment for the record. So having this written down allows you to not have to memorize it. And this is the most intimidating equation in all of algebra. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. One of the most intimidating equations in all of algebra because it involves every math operation that you've pretty much done up until this point. There's addition, subtraction, square roots, squareds, division, multiplication. It's got it all. And you can revisit those explanations in first semester. I talk about like where this formula comes from and that kind of thing. But you can revisit that stuff from like first semester resources. For right now, let's just suffice it to say that this is what I'm going to be using. And you'll notice that it fundamentally solves for x. So where did these a, b's, and c's come from? Here's what I'll remind you where they come directly from. They come from the fact that I can rewrite a standard quadratic equation in the following way. Ax squared plus bx plus c, where a, b, and c are coefficients. Simply put, to translate between these two things, a, b, and c are the numbers that are in each of those places. A is the number that's going to be multiplied by x squared. Even though it's blank right there, there is technically a number. It's the number 1. B is the number multiplied by x. And c is just the leftover lone number. And you'll notice that I need to get it set equal to 0. So if particularly at this step right here, it was important that I move that 256 over to the other side. Okay. So here's where I'll remind you of what we talked about in first semester. Being able to identify A, B, and C are really that's the important step here. Beyond that, it's just going to end up being calculator work because we'll know each of these numbers. We just have to do the order of operations. So A is whatever's multiplied by x squared. That's actually going to be 1 right here. A equals 1. B is the coefficient multiplied by x. That's the positive 8 right here. Make sure you're keeping track of sign. And then C is the leftover number, the one that doesn't have any x attached to it at all. But again, make sure that you're keeping track of sign. That will end up mattering. So that's a negative 256. And now we have everything we need to solve this quadratic. I'm going to burn through this pretty quickly because this can be tedious, but it's essentially just calculator work. All right, brace yourselves. I'm going to work through it quickly. So when I plug this stuff in, I get a negative b. That's a negative 8. Plus or minus the square root. And bear in mind that if b was a negative number, I'd have a negative number, and then it would just turn it positive, so it just flips the sign. All right, b squared, again, that's just going to be 8 squared, minus 4 times a times c. 4 times a is 1, and then c is negative 256. That's going to make things a little messy here because I'm going to get a negative times a negative. Keep that in mind. All this over 2 times a, and a here is 1. That's just plugging the numbers in. So this is just kind of the method I take here. Now I just do this in like little chunks. Don't try to do it all at once. So I get negative 8 plus or minus, and here's where I just deal with the square root. 8 squared is 64. 4 times 1 times 256. I'm going to get minus a negative 1024. That negative 1024 came from multiplying 4 and negative 256. Many of my students would just simply convert this to a plus sign. I always take the time to show it's a minus a negative, so I know what I have to do here. And you can just draw a big plus sign to get rid of that. All this over 2 times 1 or 2. Keep going. X is equal to a negative 8 plus or minus. Now I'm going to get the square root of just adding these two together, 1088. All over 2. All right. I'm going to run out of time in this clip, but let me just explain that you're going to get 2 solutions here because of this plus or minus. All right. Because this plus or minus, I'm going to get two solutions, so I'll explain that after the recording finishes.